Alright, so now we can also look at, there's kind of a pattern. We notice that terms 1, 3, 4, and 5 are all basically linear. At least linear with respect to our random variable. So these are all going to work out the same way. So let's write all those out first before we go to term 2, which is our nonlinear term. So term 3, very simple way. This is our pressure term. This is just going to be our minus ddxi of the ensemble pressure plus our deviation in pressure. And for this, if we apply basically our rule 3, we average it. We then apply rule 3, which lets us move the derivative outside of the average. We then apply rule 2, which lets us break everything up. And then we apply rule 4. We can show that basically this is just going to be equal to minus partial derivative with respect to xi of the ensemble average pressure, as this is going to go in a very straightforward way. Same thing with term 4. Term 4 is our viscous term. So this is 1 over Reynolds number times second derivative of, with respect to dxj of the ensemble average of ui plus ui prime. What we basically have here, we are going to take the average of that, right? That's what we actually have, so we need the average of that term. And if we do the same thing, we apply rules 3, 2, and 4, we can show that the prime will go away, and this will also hold for the average, so that this will just be simply 1 over RE, 1 over our Reynolds number, times second derivative with respect to dxj of the ensemble of ui. So we'll just basically hold for the mean as well. And then term 5, if we just average that, we didn't decompose it because it's a forcing term. Well, this is kind of where we now have the average of Fi. If Fi is a constant in each direction, say it's gravity if it was a body force that we have in this case, then this by just rule 1, which by the way we also have to, I guess technically we need to use rule 1 here to move our Reynolds number out front there. If we use rule 1 here, then we can just show that this is basically just Fi. So if the forcing is already a constant forcing, then it stays as a constant as we move through it. So term 2 is the only one that really has much to it as we go through it. So term 2, we have basically that dui, duj, right, we're talking about this term, our nonlinear term, dxj, which we decomposed to show that it was the partial derivative of the ensemble of ui plus ui prime times the ensemble of uj plus uj prime divided by dxj. We're going to take the average of that, right? But before we do that, actually, let me step back for a second. Before we take the average of this, let's multiply this out. Alright, let's get everything combined together so that we can write this as ddxj of, we'll have a big kind of mess in here, and we'll have ui, the ensemble of ui, times the ensemble of uj. Alright, multiply those first two terms together, plus we'll have ui prime times the ensemble of uj, plus uj prime times the ensemble of ui, plus uj prime ui prime. right? We now are going to take the average of this. So we're going to take the ensemble average of this. So basically we're going to add this term to it. And if we do that, we can use, right, first thing we need to do is we need to move the ensemble average inside the derivative. So what is that? That's going to be rule 3 to do that. And if we do that, we now have, let's just write that out, we'll have dxj of the average of ui, of the ensemble average of ui uj, plus the average of ui prime times the average of uj averaged, plus uj, the average of uj prime times the average of ui, plus the average of ui prime uj prime. Alright, as we go through that. So now if we look at this, in this case, for our given averaging defined average, this is a constant. ui, the ensemble average of ui is a constant with respect to the ensemble average, and the average of uj is also a constant. So this first term, basically by rule 4, we can write as ddxj times the ensemble average of ui times the ensemble average of uj. What about the second term? Well, again, for the second term, by the same rule, so now we're basically going to liberally apply rule 4. All right. But this next term, this uj is a constant with respect to the ensemble average, so that what we really have here, we move this out, and this term can actually look like the average of uj times the average of ui prime. Well, by rule 4, the average of ui prime is 0, so that this term goes away and this entire term is 0 for averaging rules. Same thing happens for this term, and in the same way, ui is constant with respect to the ensemble average, so that we really can view this as a constant times the average of uj prime, which the average of uj prime is 0, so that goes away. This term, there's really nothing we can say about this term. So although we have those rules, this is actually two fluctuations multiplied together, so there's nothing that we can do to basically look at that one. So we have that term still left, so we'll have plus dxj of the ensemble average of ui prime times uj prime. That will be left in that component there. Now, this term in particular is an important term for turbulence. This is basically what we will define. So u I prime times uj prime is usually termed as the Reynolds stress. And it's a tensor, right? We have 2 free indexes, so that means we have 9 possible values. So this is going to look good. This is going to be a tensor quantity. And when we talk about, this is an unclosed term. So this term is an unclosed term in the equation. Basically, it's a new variable. Right? We've added a new variable to the list, which is this new stress that we didn't have previously. And in general, this is referred to as the closure problem for turbulence. So basically, when we try to represent our flow now in terms of its statistics, basically its average and the fluctuations from that, we run into this general problem that we create as we go through the equations. We end up creating new variables that are new unclosed terms.